Hey, welcome to the next update. Today I worked on serial communication, specifically over UART, like I may have mentioned in the last video. I implemented a new module, Dang serial. It took me a while to figure out how to do this one, because the first thing was to get the divisor here, which took a bit. Needed to read into it, look up what the number was supposed to be. And then I found out that you need to take your master frequency, which on this board currently is 100 megahertz. So take it as 100 million and divide it by the baud rate that you want. And for me, that was 115,200. And that results in approximately 868. So the divisor is 868. This is required for UART. You need to split your clock into like these smaller chunks, so to speak, because it heavily relies on timing. And then the body is pretty simple. You can see that the whole thing is like, wait, where's my cursor? Yeah, the whole thing is like 40 lines. So this is a relative offset, actually. Wanted to mention that some people ask like, hey, why are the lines so weird? And so my cursor, the current line, and all of these are relative. So if this is Neovim, and you can navigate quickly by seeing, okay, I'm on line 28. Okay, now I press 10 and I press J or K, and I can move up and down very quickly, and it saves time. So thought I mentioned that. Some people asked. Anyway, so the logic is pretty simple, and we take in the master clock, we take in a reset. I'm actually not using the reset, that's why it's showing a warning. I had it tied to the CPU reset button that's up here. No longer needed. I'm actually going to remove that. Then we take in a byte, whatever we want to print. This is an ASCII character, or could be anything really, but it's supposed to be for ASCII characters. And then we do the divisor, like those are the inputs. We do the divisor, and then we have a previous. I'm also not using that anymore. I wanted to deduplicate the printing, so whatever character we get, we check what the previous character was, and if they're the same, we don't print. If they're not the same, we print. I disabled that here, so now we print all characters. You're gonna see it in a while, in a bit, I mean. And then we shift. So UART has 10 bits. It has a start bit, it has a byte in the middle, and a stop bit. It's LSB, so you start basically from the other side. It's like inversed. And then here we have the body. You can see this flip-flop always. This depends on the clock, and this also requires the storage of state, which means that we have to use a flip-flop. We can't use combinatorial logic here. So it needs to be this assignment, this kind of like the angled bracket and equals, because we need to maintain state. And so we shift through all the bits, and then we're done. The UART protocol is idle high, so basically it's high when it's idling. So when we're done, we just keep it at all once, and that's basically how it works. And the actual characters transmitted are just ASCII characters, 1 byte. I'll show you in a bit. I mapped it to the switches so that it would be easily demonstratable. So let's open up a serial console here. I have picocom configured. You can see baud rate here, and the rest is default. You have 8 data bits, it's 1 byte characters, stop bit 1, focus, okay. We have no flow control, and the rest is pretty much irrelevant and defaults. So it's ready, we have it connected, and Now, the encoding of the letter A, capital A in hex is 41 in hex, which means that we can decode or convert, if you will, the 1 and the 4 in hex to binary. To do that, we start here. So the 1 in hex is just 1 in binary. We flip it. And now we find which one is 4. So we do, it's not in the first 4. So 1, 2, 3, 4, because we have the first character. Like these first 4, 1, 2, 3, 4 are representing the 1, but only this one is true. Then the next 4 are representative of the other piece, which is the 4. So if you can see it well here, it's kind of bright, this light. I'll need to bring it down a little bit. There's a way to do it. 1, 2, 3, 4. So 1, 2, 3. So this one will turn on. I need to do it using my hand. So now you can see that we have 1, 0, 0, 0, 0, 0, 1. And that's hex 41. And indeed, we're printing infinitely capital A, hex 41. That's the ASCII of capital A. Simple as that. We could do B by doing this. This is kind of wonky. There is something with terminal control characters that's kind of like messing it up, but you can see the B there. So it is transmitting correctly, but there's something off with the with terminal control characters. Ignore that. You can see the B in there. We could do C, add 1. Now you can see the C in there. Ignore the rest. So I'll still need to figure out that this will eventually work because I want to transmit strings eventually. Initially, it's going to be used for singular characters. For example, if I need to debug something, like for example, which opcode is being executed, instead of using the LEDs, which I had to do up until now, I can use serial instead. So that's the purpose. Mostly singular characters or 4 bits. Nothing more. So no strings. This is not that much of a problem for me right now. I'll fix it later on once I actually want to use serial to transmit bigger things, like for example binaries. That's gonna be absolutely necessary to fix this before then, because I think it could actually mess with the stream. So right now it's just, you can see that this one LED is TX. It's transmitting all the time in a busy loop pretty much, and the next there's one next to it here that's RX. When I press my keyboard, you can see it flashing. When I hold, flashes. This one is not wired in yet. Well, technically it is wired in, but it's being zeroed. So it is wired into the DLU, but it's not actually being used anywhere. Which brings me actually to another thing to show you, which is the memory controller now. Here. So you can see that at this address here, we have serial in, and if we look up here, we have serial out. These are mapped. This is still core IO, so these are hard-coded. But once I have expansion cards, like sound cards, VGA cards, stuff like that, there's going to be an interface that's going to be mapped here, and all these things are going to be plugged into that interface, all these expansion cards. But this is core IO, so this is just hard-coded in. It was similar on the i386. There are ports for like the PIT, for example, or the PIT, the keyboard, stuff like that, that's hard-coded into it. So these things are just the core infrastructure of the platform, so it makes sense to just bake them in. So you can see, and adding new ones is as simple as mapping them to some predefined address in the IO range, which I think I showed yesterday. So as simple as that. Anyway, quick update, and the next step is probably writing the expansion interface. I would like to do that so that I could write a very simple sound card. It'll all live on the FPGA for now, but later on I want to potentially use these PMOD headers. So a sound card, and I want to play 8-bit music. I find that very fascinating, and I would like to get that working, and I think that would also provide some extra value. You could hear it playing. I think it would be pretty cool. So that's the next step. I think that it's going to take a bit longer, because first I have to work on the expansion interface, and then on the card itself I give it like a week or something. So potentially a next video there, until or unless I reorder things and do something else before doing that. So we'll see. Anyway, thanks for watching.